Okay guys, thanks for joining. We're going to try to do a short lesson here on two things. One is arithmetic sequences and geometric sequences. Okay, in one case, some people call it arithmetic sequences, but I think it's technically pronounced arithmetic. But it's where you have a series of numbers that are separated by a common difference. Okay? By a common difference. The definition of arithmetic sequence is found in your book, and let me just read it to you here. So it comes from chapter review question number 31, and the answer is a sequence in which the consecutive terms differ by a constant value called the common difference. Okay, so let me just make one up here. So here is one that is separated by 2. So to get to the next number, we just add 2, right? And this continues on. So to go from 2 to 4, we add 2. Well, that's pretty obvious, okay? So this is arithmetic. Okay, now let's start with the 2 and show you what a geometric sequence is. So the first two terms of the geometric sequence are going to be the same as the arithmetic sequence. So 2 times 2 is 4. But now you start to see a difference. So multiplying 4 times 2, you get 8. And then 16 and 32. So this one grows a lot faster than the arithmetic sequence. This is a geometric. Okay, the definition of a geometric is a sequence in which the consecutive terms differ by a constant multiplier called the common ratio. Okay, so here, this 2, the adding of the 2 is what's called the common difference. It's a positive 2, and the common ratio was a common multiplier. It's a positive 2 as well. So we let D equal the common difference, and the R is equal to the common ratio. We're going to use these letters here later on as we try to create a generic form of this equation. So kind of keep those letters R and D in the back of your mind. They're called common difference and common ratio. Okay, so let's take a look at some problems in the book, and then we'll probably come back to these. And we're going to define, there's two ways to define the sequence. One is what's called a recursive formula. And there's another form called the explicit formula. Okay? Or explicit form or formula. Okay, so there are two different ways. And let me just talk, since I already started this example here, let's just talk about the recursive formula. It starts with a sub n. Now, a represents kind of a position, and n is the position number. So n is a variable, it changes, okay? So let's say, so n can be any whole number or any counting number. Rarely is it 0, and rarely is it's never negative. So just think of positive counting numbers here. So if I put a subscript on n to be 1, this is what's called the first term in the sequence. And in the first sequence above, the first term is 2. The a sub 2 is the second term, and on and on. Okay, so the way the recursive formula works is it's by referencing the previous term. So if n is a variable, then n minus 1 would represent what's called the previous term. Okay, so again, I know that it's kind of confusing because n is changing, but if, let's say, we define n to be 3, then n minus 1 would be 2, right? Because 3 minus 1 equals 2. Okay, now to do the recursive formula for a arithmetic sequence, what we're going to do is just add the common difference, okay? So in the case above, in our first arithmetic sequence, we're going to just simply say a sub n equals a sub n minus 1 plus 2, because our common difference was 2. So that is actually all you have to do to define the recursive formula for an arithmetic sequence. Okay, now when it comes to the explicit formula, and we'll talk about recursive formula for the geometric in just a second, but let's talk now about the explicit formula. Okay, for the explicit formula, this can be found on page 155 for the arithmetic sequence, and here is the generic form. A sub n equals a sub 1, so that means the first term, plus, and just go with this for right now, I'll explain it in a second, it's n minus 1 times d. Okay, so basically what this says is it says, okay, you give me the first term, which if you look above, the first term in both sequences was 2. So you give me a starting place, and then I'm going to add, depending on which position it is, okay, I'm going to multiply n minus 1, so it's 1 less than the position number, and this is a little bit confusing, but our common difference was 2, so we know that's 2. Let's talk about this n minus 1 here, okay? So let's say that we wanted to, let's just kind of check it. Let's say we wanted to find the fifth term of the sequence. So we're going to plug in 2, that doesn't change, but for n we're going to plug in, this is n is 5, and then we're going to multiply that difference, which is 4, times 2, which is 8, and then we're going to add 2, which is the original, or the A1. That's the starting number. So according to this, this would be equal to 10. So the fifth number in our original sequence at the top should be 10, if we got it right. And I think we did. So this is A1, this is A2, this is A3, this is A4, and this is A5. Okay, so why do we use n minus 1? Okay, so let me try to explain it this way. For our first term, right, it's going to be the first term according to this equation, and if we plug in 1 minus 1 times 2, we get 0 times 2. So basically all this says is that the first term will be the first term. Okay, and as you kind of move down the list, then it kind of makes a little bit more sense. So again, for the second term, it's going to be the first term plus, and this is going to be, this that goes in here is going to be our multiplier. Okay, so it's going to be multiplied by 2. In the case of 2, it's going to be 2 minus 1. So if n is 2, it's going to be 2 minus 1, which is 1, times 2. So basically all this is kind of doing is it's just setting the stage so that we can add a constant number, but it's going to be multiplied as we move from the first term to the second term to the third term. This number right here, let me circle it in red, this number here, the n minus 1 term, is going to be increasing. Everything else is going to be staying the same. Okay, so the first term is always 2, and we were just checking it here to find the second term. The second term should be 4. Oops, the second term should equal 4, and it does if you go back up. Okay, so let me just recap. Somewhere in here we have the explicit formula. I think it is right here. This would be the explicit formula. And sometimes it'll ask you to simplify the explicit formula. So all of this was just explanation. So let's skip down here and simplify. So it's 2 plus n minus 1 times 2. Let's rewrite that. If we can, just a second. Let's get down here. So we're going to take that formula or that form and we're just going to simplify it. So it was the first term, what we called A1, plus n minus 1 times d. So this was 2 plus n minus 1 And the common difference was 2 in our example. And this was a sub n. Okay, so we're going to distribute, use the distributive property, distribute. So multiply 2 times n and 2 times -1. So we get positive 2n minus 2. And then we have a 2 here. So this is just what they call it, a simplified form of the same thing. Now what happens here is these 2's are opposite in sign. So we have a simplified form. It just says 2 times n. Now the way this works is you can plug any number in for n. And so if we want to find the 10th term, n is going to be 10, right? All we have to do is multiply the number times 2, and we'll get the number. So the 10th term should be 20. Okay? So you can see that seems to be true, because if you take the term number, the n number, multiply it by 2, we get the actual number. So we get the position multiplied by 2, and it gives you the actual number in the sequence. Okay? Now let's take a look at geometric sequences, and then we might do some examples, some more examples. Okay? So for the geometric sequences, if you look in your book, the recursive formula is found kind of hidden. It is kind of hidden on page 159, and kind of in the middle there. The recursive formula is equal to a sub n equals a sub n minus 1 times r. And so all this says, it says basically the next term, or the term that you want to define, because n is going to be a variable, it's going to be equal to the previous term, the term right before the nth term, times some common ratio. Okay? Okay, so like in the first one that we looked at, let me just highlight it here. We looked at this sequence here, 2, 4, 8, 16, 32, and 64. We said our common ratio was equal to 2. So if we were using that example, we would just say that the recursive formula is just n minus 1, a sub, and then it's a subscript here, n minus 1 times 2. That's it. That's all you can do with the recursive formula. It's not really useful in determining what the next term is. It just says that the next term is equal to the previous term times 2. That's all it says. And of course this variable, the common ratio, can change. Let's look at the explicit formula. Let's explicit form. This one is a little bit more useful. Okay, the explicit form is going to be found on page 160, and it's a sub n. A sub n equals a sub 1, so the first term, times r, the common ratio, raised to the power of n minus 1. Okay, so this n minus 1 is going to tell us basically how many times we need to multiply r. So maybe it's 2, maybe it's 4, maybe it's, a multiple. So r is going to be multiplied by itself multiple times. So in our form, in our sequence above, I think we started with 2, then we went to 4, then we went to 8, then 16, then 32, and then 64. So I'm just multiplying each term by 2. So we said r is equal to 2. So let's plug in 2 for r. We also know what a1 is. a1 is the first term in the sequence, which was also 2. And so the only thing we don't know, and we're going to leave it like this, it's n minus 1, because that gives us variability. So we have now defined first, what, 6 terms of this sequence. So we could check it. This is the 5th term, and then 64 is the last, or the 6th term. So if we put in 6, we could check it and see if it works. We should get 64. All right, so n is equal to 6, so n minus 1 is just going to be 5. Okay, so we're going to have 2 times 2 times 2 times 2 times 2 times 2. So we should have 6 2's multiplied. And if you want to use a calculator, you could just do 2 to the 6th power, which is 64. Okay, so it checks out. So right here, I'm going to put it in a box. This is your explicit formula. Okay, so now we've defined the recursive formula for a geometric sequence. Okay, so it takes on this form. We have defined the recursive or the explicit form for the geometric sequence. Oops. And then we've also done the same for the arithmetic sequences. Okay, so since this video is getting a little bit long, I think what I want to do is I want to stop it here. And then in the next video, I'll kind of have some examples from the textbook. I'm going to go with examples, so see how this actually plays out in example by doing some problems in the book coming from chapter 4 review. And let me give you a page number. We'll start with problem number 34 and we'll work through to 43. So chapter 4 review is on page 177. Okay. All right, we'll stop there and I'll pick it up on the next one for the examples.